dynamically balance the moving parts on a microscopic level. What does this mean, anyway? When a structure is dynamically balanced, it responds accurately to the forces acting on it without additional vibration or resonance. When a structure is not dynamically balanced, it responds by ringing or resonating, like this bell. All materials have modes of resonance. That's how we hear the bell. Different materials resonate at different frequencies, but every material, when we add energy, will resonate. When materials in a loudspeaker resonate, independent of the musical signal they're trying to reproduce, they add distortion, which we hear as a coloration or a loss of clarity. A loudspeaker should only reproduce the sounds sent from the amplifier as they were sent, not the additional resonance. It might be easier to demonstrate this if we look at a structure that's larger where we can see the phenomena, one that's not dynamically balanced.
This is historic footage of the Tacoma Narrows Bridge, built in 1940. A few months after its dedication, the wind reached the exact speed that excited the natural resonant characteristics of the bridge, 42 miles an hour. When the wind added the necessary energy, the bridge resonated, causing its collapse. On a microscopic level, the same distortions happen on the surface of the loudspeaker when energy is added. The laser interferometry measurements done at the Johns Hopkins lab allowed our research engineers to study modal resonances on a speaker cone and objectively measure the effect different materials would have on those resonances. These graphs represent the modal resonance on the surface of the speaker cone. The flatter the surface of the graph, the less modal resonance present. This cone is made of a material showing a high level of resonance. This cone assembly measures poorly also. One of the first things we discovered was that no single material could solve every problem.
There are several critical factors in the choice of materials for loudspeakers. We have to consider the mass of a material, the stiffness, the geometry, and for loudspeakers this all adds up to the modal resonances. We could choose a material like aluminum. Aluminum is strong, very stiff, good strength to weight ratio, although it's not particularly light. And we can put it in geometries that make it very stiff even more. However, when aluminum resonates, it does it with a vengeance. Now there are other materials called polymers, which have characteristics, some of them at least, that help reduce the resonances within the materials. They have high mechanical losses. Here's one. We can even put it into a structural shape so that, although it's not as stiff as aluminum, it's still strong. And when we strike it, what we see is that the resonances are reduced. But what we can also see and hear is that there's some resonances left. And what we've done in large part is reduce the resonance but also moved it down in frequency. Now this is only a problem because humans hear all the way down to the bass, all the way down to the very low frequencies. If we take these two materials, however, one of them with surprisingly and alarmingly different characteristics than the other, and we put them together, we create something we call a composite structure. What happens is that the material characteristics fight each other. They create a structure where each one wants to control the resonances within the materials. As vibrations move through the materials, at the interface between them, they work against each other. They turn the resonant energy into heat. What we have is an almost completely non-resonant material that we call a composite structure.
After exhaustively testing a wide range of materials and analyzing their performance, we developed a composite material that showed a tremendous reduction in modal resonance. The flatness of the graph demonstrates the success of this composite material technology.